All right, well, good afternoon, everyone. Thanks for joining today's webinar on how to build and secure an Edge AI solution presented by industry leaders Arcturus, ARM, NXP, Siemens, and Synopsys. My name is Peter Anselmo. I'm the Business Development Director at Electrosource, and I'm co-hosting with Mike Nicoluk, who's the President of Electrosource. We're an ecosystem sales and solutions partner for these world-class companies. Today's presentation will cover architecture considerations for both hardware and software, from IP cores to system on chips to operating systems and AI algorithms, and finally securing your software applications. Here's our agenda for today. We have a great panel of speakers who are industry experts in the topics being presented, and they'll introduce themselves in just a moment. The presentations for each speaker will be about 10 to 12 minutes. There'll be a demo by Arcturus, and we'll close with a Q&A session at the end of the webinar. We ask that you please type your questions into the chat window, and an email will be sent with the recording and presentation to everyone approximately 3 business days following the webinar. Here are some of the key themes that we'll cover today throughout the presentations. ARM's hardware device model. This is commonly used in IoT edge devices, anything from a microcontroller to an application processor, or even an NPU or neural networking processor used in today's devices are using this model. Secondly, software security at the operating system and at the application layer, ensuring that device software security at the edge and through the software development lifecycle. Arcturus will show an AI edge video delivery platform using AI and ML machine learning algorithms that run on NPUs using model optimization and video pipeline deployment. And then finally, containerization, frameworks for developing, delivering, and securing a container strategy for the edge. Each company provides platform frameworks for these technologies to run on these technologies and also help you to get to market faster. Another key theme that you'll see throughout the presentation is this partner framework which the group has put together. This represents elements of a secure edge solution, which you'll see throughout the webinar. And this is the foundation for the hardware and software security that was noted in the title. So with that, I'll hand over to Reid and to start the introductions.
Thank you, Peter. My name is Reid Hinkle. I'm Digital Transformation Architect at ARM. Look forward to talking to you today about ARM's IP that we supply to our fine silicon partners like NXP, and also a bit about our architecture specifications for security and for software portability called Cassini. So I'll turn this over to Ollie Orrs from NXP.
Hi, everyone. I'm Ollie Orrs from NXP. I lead the global AI and ML strategy and technologies. I'll be touching on generally the stack just above what Reid introduced in terms of the IP of how we put that together in the SoCs and some of the standardization around certification that we deal with to allow our customers to scale up and down or along our roadmap and our processor portfolio.
Hello, everybody. I'm Scott Morrison. So I'm the General Manager of Embedded Solutions at Siemens Digital Industries. And I'll be talking about the next layer up the stack, which will be the operating system. And I'll also discuss some related topics like the remote management, monitoring, and updating of the embedded or edge device.
Hi, folks. My name is David Steele. I'm the Director of Innovation at Arcturus. We're an edge AI and vision company that provides enablement, analytics, and hardware. We focus on building solutions on top of ARM using NXP silicon, and of course that are underpinned by Linux OS and software packages that are supported by Siemens. During my portion of the presentation, I will cover the edge AI and vision aspects of the system, and I'll cover some key design considerations and give you a couple of demos of what you can do and how you can do it. And then I'll hand things over to Steve Chappell from Synopsys, who's going to talk to you about how you can ensure the system is secure and protected.
Great. Thank you, David. I'm Steve Chappell. I'm the SE Manager and a Software Security Evangelist at Synopsys in our Software Integrity Group. We provide tools, services, and education in the areas of software quality and security. And I have the pleasure of trying to condense all of our countless person years of experience into 10 minutes of best practices and getting started tips for securing the software and all the parts of the edge and adjacent systems that we're going to be building up today. So I think with that, I give it back to Reed.
Reed, you should have control privileges. Let me know if you do not.
For some reason, not working.
Okay.
Okay, so today wanted to talk a little bit about the problem statement, but before that, just briefly on ARM. For any of those who are not specifically aware, ARM is an IP company. We license our IP to a broad number of customers, including several of those on the call today. Most notably the processor IP that are powering many of the devices in the market today, everything from 32-bit microcontrollers, where the #1 IP platform for microcontrollers, all the way up to 98% of the microprocessors in phones, but also the applications that are powered in the cloud, including the new Graviton3 processor that's used in many of the fastest growing cloud instances in AWS. And last but not least, the fastest computer in the world, the Fugaku in Japan, is currently the title holder for fastest state hyperscale PC. So the problem statement, when you think about that, from everything from the rich endpoints to the cloud and data center aspects, are that it's critical to be able to scale this, all the new applications, all the new use cases. We need to create a frictionless edge to unlock the value, particularly for around IoT platforms. So on the left hand of the scale here, we have the what happened?
Not sure. I'll put it back into sure.
Sorry about that. Sorry about that. So basically massively distributed, very diverse and heterogeneous compute. And then on the right side, very centralized, connected and homogeneous compute. So the problems are quite different. But what we're finding is that from an architectural perspective, we can use many of the same attributes of an architecture of the hardware and firmware to be able to create this frictionless environment. So our aim is to basically create acceleration where hardware meets software. And we have some initiatives that span across the various different use cases that you see across the top. So on the autonomous automotive, robotics, and edge infrastructure side, we have SoC, including the manufacturing 4.0. So anything where you're doing mixed critical capabilities in a device where you need not just security, but also safety. That's where SoC comes in. And then we have ARM Total Solutions, which are basically providing all these hardware and software infrastructure for delivering end solutions. So this is really what we're going to talk to you about today, are the Project Cassini, which is foundational to the SoC frameworks. So what is Project Cassini? It's essentially a series of standards and specifications for how you build the hardware and firmware that we deliver to our silicon partners and our software ecosystem partners, to assure that they can build platforms that can host edge or cloud native at the edge capabilities, meaning that you can run very modern applications that have traditionally been available only in the cloud at the edge. And this could be things as lightweight as, from a Cortex-A or a applications processor, as green grass functions, green grass Lambda functions, all the way up to containers. Obviously, in an endpoint device, you're not talking about full cloud workloads, but you are talking about applications that can be containerized and delivered to the edge. And that's basically what we're going to be talking about today. So just to give you an idea of the ecosystem engagement targets, so we have a variety of silicon partners, software vendor partners, ODMs and OEMs, and then system integrators. Some of our key partners today are here joining in the call today are NXP, Siemens, Arcturus, and Synopsys. So just a bit more in depth of Cassini it consists of ARM System Ready, which is the hardware and firmware specifications. It comes along with a certification program. This program is intended to assure that we can actually deliver the quality of service and the expected capabilities of the platform. We also have a security certification program called PSA Certified, which basically assures that your product meets the standards and best practices of a secure product intended for the IoT market. And then we have Parsec, which is a security abstraction and microservices layer, which allows basically any workload, any OS, any function that is operating in the non-secure world to have access to secure world security functionality, including secure storage of key material and certificates. All of these come together to deliver the cloud native stack experience. In terms of the additional piece, we have the system ready advocacy. That's part of what we're actually doing today, and we work across our operating system and ISV partners, cloud, telco, and enterprise OEMs, IoT infrastructure enablement companies, and system integrators to be able to make sure that the full value of Project Cassini can be realized by end customers. From a Parsec perspective, we have a number of partners that have already adopted the technology. We actually co-founded the project with Docker, and now as examples, we have Debian and full Yocto support for Parsec. So System Ready, just in brief, is the foundational compliance certification. It's focused on the most common components of the software stack, the OS, hypervisor, and middleware components, so that these just work, enabling partners to focus on their innovation and acceleration in deploying different application layers of the software. It is the foundation of Project Cassini, along with the PSA security and cloud native experience at the edge. So it's aimed at simplifying the landing of OS distros on the platform. And so basically we have the different silicon partners or SoCs are targeted at different markets. But the system ready hardware and SDKs provide a standard way to package up the SDK so that they can be delivered to the platform. Talk here a bit about Parsec. In the example here, which was the original example that we demonstrated, was enabling Docker container security operations. So to where you create a Docker container on the desktop and deliver that securely across all the way through the staging, production, and then to devices. As you can see, Parsec is designed to enable any workload in any programming language, in any container runtime, and in any packaging. And then it provides that security abstraction and microservices architecture across any platform, architecture, or hardware. And then on top of that is basically access to any way that your root of trust in a platform is delivered, whether it be TPM, HSM, or trusted application running in a trust zone. OS integrations, as I mentioned, include the Octo project, also Fedora, Red Hat Fedora IoT, and OpenSUSE, and many more are coming soon. And then we have cloud integrations that are coming soon, including AWS IoT Greengrass 2.0 support, which we announced this week at Amazon reInvent or AWS reInvent, and also Azure IoT Edge Secure Enclave Blueprint support, which we debuted at ARM Developer Summit in October. Last but not least is ARM PSA device model and the enabling AI, machine learning, and trust. So this is the core of what Peter had mentioned today, where we basically show the stack up of how secure platform can be delivered to end customers. So at the base, we have the untrusted resources of the SoC. Then you build the platform root of trust, both in its immutable and updatable form. And then that's becomes the basis for enabling our partners like NXP to create their AI and Arcturus on creating their AI ML pipeline and implementation, which is built upon the Siemens OS and all the security features of the OS, and then delivering up to, once all these elements are pulled together, then we have support from our fine partner Synopsys on how you can actually take and evaluate the secure implementation of your platform. Now I'll turn over to Ali to speak to you more about NXP.
Great, thanks a lot, Reid. And perfect. So NXP is the embedded processor vendor in the mix in today's webinar, and for us, we leverage the IP from vendors such as vendors and partners such as ARM, as well as some of the building block certifications that Reid also touched on. We have a very broad range of processors, starting at the lower end from traditional microcontrollers with ARM Cortex-M cores, at times multiple cores, very rich set of I/O, and some embedded memory, typically in our Kinetis and LPC family of devices. We also have a class we call the crossover microcontrollers in the i.MX RT family, which combines superior computing power and multimedia capabilities, as well as real-time functionality. So these devices, such like the i.MX RT1170, for example, have very high, we call it record-setting speeds in the 1 gigahertz for the Cortex-M cores and the Cortex-M7, and can be applied to a very wide base of applications and use cases. And at the higher end of the compute performance, we have our i.MX applications processors and Layerscape processor families. These typically have Cortex-A CPU cores, multitude of them. They might have GPUs for graphics, DSPs for audio and other signal processing applications, as well as, starting with the i.MX 8M Plus, we now have the NPU machine learning accelerator core being added to these devices, and most of them going forward will have an ML accelerator as part of the overall architecture. Our ARM-based portfolio offers very high levels of integration, comprehensive software and hardware enablement, and a broad range of performance. The processor continuum, as we call this, allows our customers to select the optimal device for the current needs they have, but also allows them to scale up in performance if needed, or scale down to a more power or cost-efficient device as their need and product versions might require. The aspects of ARM's project Cassini that Reed touched on, describing ARM system ready certification and PSA certification, are part of NXP's commitment to enable this ease of scaling. So as we saw with System Ready, it implements a set of hardware and firmware features that allow the operating system can depend on, that allows it to just run. So easily deploy operating system images and just run. This is across the portfolio for NXP. Similarly, for the PSA certified program, we have multiple devices in this NXP continuum that both in the i.MX RT crossover microcontroller series, as well as the application processors, the i.MX 7, the i.MX 8, and i.MX 8M series that are certified and offer reassurance to our customers that the product security has been tested and it's ready to go, and it's a secure IoT target as needed. The new device in our portfolio that was just announced, it's been announced as a family, the i.MX 9 family. So this has a set of enablements similar to with Edgelog Secure Enclave. These are ARM A55 based host processor devices with ARM's dynamic IQ technology. It's more efficient and higher performance than the A53 across the board in a lot of metrics. It has the 9 family also has built-in MCUs to assist in real-time processing and supporting very low power, always on modes. So you have both a device and an M Cortex core, providing scalable compute as well across the family. The 9 series also has the Edgelog Secure Enclave. So this is really about evolving security beyond just a crypto core. You have on-die security with real-time attestations, silicon root of trust, trust provisioning, fine-grained key management, and a simpler path to overall security certification. And with the Energy Flex architecture that we support, you can actually independently power on and off each domain, the application domain with the Cortex A cores, and the real-time domain, the Cortex M core, as well as the actual Flex domain, which has the multimedia and neural processing accelerators, can all be controlled separately. And within this device, moving a bit faster than it should. So as I mentioned, we have the Cortex M core domain, the Cortex A, and we're also adding an Ethos US65 micro NPU from ARM's ML accelerator portfolio. And this is a very efficient small memory footprint accelerator for 8-bit integer machine learning acceleration. And it leverages the NXP EIQ machine learning software development environment that I'll touch on in the second half of my discussion around the enablement for ML that NXP put together. The reason why we're on NXP's portfolio, we're looking at actually having integrated NPUs across the board in our devices is summarized by this chart. This is based on the 8M Plus, which was the first device that had a dedicated machine learning accelerator in NXP's i.MX portfolio. And here you can see that compared to a CPU core, the NPU for quantized models, 8-bit quantized models, is achieving an over 18x acceleration for a set of classification and detection models, so machine learning models across the board. We're seeing 18x, 30x, 25, all the way above 40x acceleration on the NPU versus the CPU core. So as we see a lot of proliferation of ML workloads, we're offloading the CPU main compute with a dedicated accelerator for these types of workloads. And then to enable that heterogeneous compute element, we've built out our EIQ machine learning software development environment. So here, NXP took an approach of providing a full machine learning development environment, all the way from data preparation, collection, training, and data curation, to validating, training a model, validating it, converting it and deploying it onto a device. But we also kept it fairly modular so that our users can use their, if they have already external preferred tools or they have their own scripts, they can pick and choose as much or as little as they want to from the EIQ toolkit that NXP provides for ML application development. And this is what we call the EIQ machine learning software development environment. So we have the goal to enable a very wide and broad range of experiences from our user base, from experienced ML experts, data scientists that know very well what their preferences are, what they're trying to build, and have a lot of experience in the domain, to embedded developers that are just starting off in their first or are early in their ML journey. And the tools scale with the experience. So we provide a GUI-based environment with the EIQ portal to build vision-based ML applications. The toolkit assists with the workflows, either working with your own data or bringing in a pre-existing pre-trained model and converting it into an optimized format supported by NXP devices. And again, deploying it into the runtime with EIQ inference options, both from an open source environment, such as TensorFlow Lite, TensorFlow Lite Micro for microcontrollers, Glow compiler. And to this, we've also added a proprietary inference engine in what we're getting from our close partner Ozone Technologies called DeepView-RT, which is proprietary to NXP devices and provides an inference engine that is that we can guarantee support and maintenance for compared to open source variants. And all of this enablement is baseline enablement that has no additional license fees from NXP's perspective to our customers. And going back to where we started in terms of the processor continuum and how we're enabling machine learning on NXP devices, this is the overall support chart that we have in terms of the compute engines available in each of our devices and which ones are enabled with which runtime, machine learning runtime inference engine, a cross-check really between a large part of the portfolio in the i.MX RT microcontrollers, as well as our applications processors in the 8M family, looking forward with the i.MX 9 family, starting with the 9.3 being enabled. And with that, I'm going to hand off to Scott to touch on the OS side, so building up on the layers and the software enablement.
Thanks, Ali. So as mentioned previously, I'm Scott Morrison. I work with Siemens Embedded. Most of you probably know Siemens is the largest industrial equipment provider in the world, but kind of less known as we are one of the largest software providers in the world as well, everything from design tools all the way down to embedded software. So the previous speakers talked more about the what we consider the base level enablement of the hardware and the software, firmware that they provide, and open source software. And it's really kind of a deep collaboration between ARM and NXP and Siemens Embedded that has literally been going on for decades, that allows us to provide this operating system solution tightly integrated with the hardware and then customized for the the end product and customers' needs, that allows them to focus on their differentiation, which is the application and the total product experience. So if I Peter, have you passed control?
You should have. There seems to be a little bit of a delay, Scott. So hopefully you have that now.
Okay.
There it is. It just switched over.
Yep, just switched over. Thanks very much. Okay, I just want to start out at a very high level and just talk about like a commercial Linux solution. Many companies decide to go with a commercial provider for a variety of reasons. Others still download and put together their own solution. So just to kind of differentiate the two options. So a commercial Linux is basically an entire solution, a package solution that comes from a company like us that pulls together, what we would consider all of the appropriate open source packages, integrates them, tests them, and gives that robust kind of operating system platform solution. Also providing customization services, so we can do feature extensions, optimizations, power management, and port it and support it on, once again, the customer's specific hardware solution optimized for their use case. And that comes with the long-term bug fixing, security monitoring, security updates, integrated tools, including working with third-party tools, like ARM's Dev Studio tools. So basically, the goal there and the offering is a complete operating system package. And for many years, probably the last 15 years, for embedded and edge type devices, these were typically based on the Yocto project. For the last few years, we've seen a lot more interest in more of an enterprise experience. And so we also now offer a Debian solution. And I think we're the only provider that offers both of those right now. So we can engage with customers and find out, what exactly they're looking for and what might fit best with their particular product and their needs. So moving on from that, obviously security is foremost in a lot of people's minds. I have a couple slides on that. Starting with kind of the overall considerations that the end customer should keep in mind, and how we can help them develop a security concept and a security solution that's appropriate for their device. It really starts at the basic level and kind of at the bootloader and the root of trust. Here we do rely very heavily on what the other two speakers were talking about in terms of hardware and software enablement, as I mentioned before, in particular the PSA certification. But what we can do is develop a kind of a customized secure boot solution for Linux, for the customer, for their hardware, leveraging the various software and hardware capabilities on the device. The next level up, once you have kind of securely booted the operating system, is to focus on various different aspects of security, and kind of prevent different types of attack mechanisms that various actors will use to try to infiltrate a device. This obviously starts with device access control. We also provide network intrusion prevention and can provide detection services as well. Something we see more and more often these days is data encryption, file system encryption, becoming quite common in embedded devices. Of course, the use of appropriately secure communication protocols, and then wrapping all of these together with kind of the vulnerability monitoring service that we have. Because when you ship the device, it can be very, very secure, maybe totally secure, but there are always new vulnerabilities that are being found over time, exploits that are being discovered. So we move on to the next slide. I just want to talk about that briefly. And Siemens has a very particularly strong practice in this area. In fact, I read a report from a third party earlier this week that said that 31% of all the ICS cert advisories that were issued worldwide last year came from Siemens. So that's almost a third. Obviously, just kind of an unmatched level of security monitoring and contribution to the enablement of secure devices from Siemens in this area. The nice thing is, we have this very, very deep and broad capability within Siemens, and we're able to offer that to our customers. So we utilize it for all of the software that we provide, and then we can also monitor additional packages and kind of customize that service for the end customer's needs to make sure that the device will maintain security over the lifetime of the device to the greatest degree possible. So just moving on from security then, talking about essentially IoT and cloud enablement for the device. There's a few different architectures or topologies that we're seeing in the market these days. If I start in the bottom right-hand corner of this slide, then this is kind of the simplest one where you have a device and it's directly onboarded and managed or monitored from the cloud or from remote servers. We call those end nodes. If you look on the left-hand side of this slide, then you'll see a more complex, but becoming more common topology where you have an edge device. And that edge device can either be a standalone device or it can further manage southbound devices. This is along the lines of what was previously mentioned as kind of that cloud on the edge capability that we're seeing more and more often. So a lot of services that were historically just available in the cloud, we're seeing those move to edge devices and being utilized for further southbound device management. And then there are a variety of services, as listed on the slide here, some of which are common to all devices, especially firmware updates, once again, to keep the devices secure, and some of which are more specific to edge devices. like the southbound management. One thing that we're seeing more and more often is a desire to use containerization services. There's a variety of different ones available, and we see those primarily, or even classify those as edge devices when they're using containerization. And there's a lot of benefits of that. In fact, the later speaker will talk about how that's utilized in the particular AI applications that he's going to demonstrate. So if we move on and just talk about Docker as an example of a containerization service. So with Docker, I mean, obviously it's very, very common kind of utilization or enablement of containerization these days. What we offer is kind of a complete workflow for the deployment and management of containerized Docker-based applications. And this starts with the actual containerization of the application, but then we package that together with metadata that can then be interpreted on the device for how the update should be utilized. Uploading it or enabling the easy upload and management of that in the cloud repository, and then triggering the actual download of the containerized application to the end node device or the edge device. And as I said, then management of the entire life cycle. So, and these things can be done, in a very customized fashion by some customers. Most people use a commercial cloud platform, such as Microsoft Azure for that. And once again, this is really becoming quite often common, and we often see people enabling this. And initially, it started with really the software update capability, but really we're seeing more and more monitoring and management of devices, and kind of the realization of the whole IoT vision that we've been working towards for so many years. And then just to wrap up, this is kind of the latest thing that we're seeing in the marketplace is a very strong desire or a need on customers' part for kind of shrink-wrapped, very robust applications. And really what we're seeing is people requiring these for a variety of different use cases. So they might need to have some mobile applications, for instance, that people are using for field service, or end users are using for basically monitoring or control of the end device, whatever that device might be. And then, of course, the more classical kind of web application, cloud application type web services, monitoring services. We partner with Mendex to enable this for our customers, because there's a lot of different ways and different languages that people can use to develop these. But the nice thing about Mendex is it's a low-code development framework that allows people to very quickly and easily develop these types of applications for either web-based kind of workstation, laptop utilization, or deploying them to smartphones or to tablets or other things, and address a variety of different use cases very, very easily in a straightforward way. And so we have a tight integration of this kind of comprehensive solution, which I would say is probably the most recent trend that we're seeing or need within the marketplace is this kind of new and very enabling, and I would say powerful type of extension of what kind of classically people view as embedded devices. So with that said, then I'll pass it on to Arcturus to talk about the next level up the solution stack.
Thanks, Scott. Let me just share my screen here. There we go. I think, can you see that now? We should have our title slide up again. Hi, folks. My name's Dave Steele from Arcturus. My role today is to talk about the Edge AI and Vision runtime portion of the platform, what it is, how you can build it, and what it can do. But sort of before I start, I think it merits saying that, we're kind of a privileged company here. It's really only because of the work that's been done across this ecosystem of partners that Edge AI is, as we know it, is even possible today. It has been through the work of companies like ARM, who've built up this broad and standardized software ecosystems, not only with things like ARM-NN, which is a neural net runtime, but also with Project Cassini, NXP silicon and low-level AI enablement with EIQ, Siemens validated OS components and packages, and of course Synopsys with their comprehensive vulnerability assessment analysis. For me, I think the takeaway, the point of this is that software systems today are far more complex than any one company can take on end to end, and it's only really by leveraging this highly layered architecture that you're going to become successful. And the flip side of that is that by leveraging it, you can do far more than you could ever achieve yourself. Okay, so let's get started. Before I get in too far, let me just give you a quick overview of Arcturus. We're not quite as much of a household name as some of the other companies today, so a bit of familiarization might help. Arcturus has been operating since 2001. We're a privately held Canadian company headquartered here in Toronto. We focus on edge applications by providing hardware, software, and solutions. We have 3 software product lines: Brink, which is our Edge AI and Vision Analytics product, and I'll dive into this more in a minute. Civic Stream, which is our solution for hardened VoIP and video communications devices, and Embarks, which is our secure IoT solution that takes care of things like firmware, telemetry, configuration, and management. And to round out our products and enable our software, we have hardware platforms, including boards and modules, and these range in scale from small ARM MCUs running RTOSs all the way up to multi-platform and multi-SoC platforms running Linux. As I mentioned, Brink is our flagship Edge AI and Vision product line. It's composed of 3 things, which I'll cover more in some subsequent slides as well. It includes enablement, which provides software and solutions to help you develop Edge AI products. It includes hardware, including our new Atlas platform, which supports up to 23 TOPS of Edge AI performance. And we also provide analytics applications that cover a wide range of use cases and markets. In terms of the use cases and markets, here are some of the areas where we see Edge AI becoming more prevalent. It's also where we focus our analytics. We have off-the-shelf analytics for smart city applications, including security and public safety. We also have analytics that describe and track people and actions. And these are really good for retail environments, for things like heat maps or creating targeted advertising. On the industrial side, tracking and characterization can be used for quality inspection. It can be used to do things like detect PPE, personal protective equipment compliance, or to provide safe operating environments, in warehousing for lifting equipment, etc. Finally, we also have experience adding capabilities like tracking and identification to high-end industrial field instruments, which is really an interesting and specialized application of Edge AI in and of itself. So in terms of our enablement strategy, this is a closer look at our software stack, and I've highlighted the core components of Brink in blue. The top layer is what we would traditionally think of as a vision pipeline. It starts on the left with video ingest, and it provides output on the right. This layer provides the front-end services and system integrations, the visualization, notification, actions, and UI, UX. It also provides the API to a system-level application or to business logic. And since this layer contains the exposed surface of the system, this is one of the key areas that Synopsys looks at when they deliver their DevOps security, which Steve will cover more during his portion of the presentation next. Now, the lower blue layer in this stack, the lower blue layer in the stack diagram contains the backend runtime analytics, ML models, ML runtime algorithms in the database. The lighter blue boxes help us to frame how some of our partner solutions fit into this, including the ARM&N runtime and NXP's EIQ enablement and tools for offline training and optimization. And of course, this whole stack is underpinned by Linux, which is Siemens domain. So at first glance, for the most part, this looks like a fairly typical Edge AI stack diagram. What makes our solution unique is the way that we have enabled, have applied containerization to it. And with ARch64, which is ARM v8, ARM has ensured standard mainline containerization support as part of Project Cassini, the Project Cassini software ecosystem. And for us, this is a real game changer, because we leverage Docker containers as a method to discretely isolate each processing node in our vision pipeline. And we can take a closer look at this approach. So here we're using a simple motion tracking pipeline as an example. Motion tracking is a very common primitive. There are almost limitless examples of when motion tracking gets applied, from retail stores to see what people are buying, to monitoring safety on a subway platform, or even for social distancing. Anywhere there is a need to provide insights on how an object or person moves over time. And in this pipeline example, it consists of 4 nodes in blue, a node for video source, a node for inference, analytics, and streaming. And these nodes are defined by classes, such as filters, sources, sinks, each with defined inputs and outputs. And then we containerize each of these nodes using Docker and interconnect them using sockets. The nodes are then orchestrated to form a pipeline at runtime using Docker Compose. So this combination of containerization, socket connectivity, and runtime orchestration translates into almost infinite flexibility. And so you might ask, why is flexibility important? Well, it's important because it makes things easy to do. Like, for example, rebalance the system by moving nodes across different processing resources, such as a CPU, a GPU, or an NPU. It makes it easy to experiment with different models or analytics simply by changing or updating a node discretely without destabilizing the rest of the system, its timing, or its synchronization. And this all has a lot of this has a lot of value to us, because when you're developing an edge AI system, one of the things you're going to discover quickly is that it takes experimentation to find the right combination of model runtime and hardware support that yields the best performance and accuracy for your application. You're also likely going to find that it's going to be necessary to enhance and adapt your applications in ways that you did not initially conceive, either to gain more insights or to mitigate some limitations that you've uncovered along the way. And finally, this flexibility is valuable because at some point you're just simply going to need to update something. So let me use this simple motion tracking example in this pipeline that we've illustrated here, just as a bit of a springboard to illustrate the benefit of flexibility. So if we think about motion tracking and we start testing it, what we might find is it suffers from some limitations. Number one is that it performs poorly with low frame rates, or when detections are missed due to object occlusions, or because detection accuracy was low, or simply because the object left the field of view for a few seconds. Once a track is lost, there's no way to recover it, and there's no way to re-identify the object at a later time or place. So in other words, while our application may require simple motion tracking may not be sufficient to meet all of our needs. So to address this, the most common approach is to generate an appearance embedding for each object as it's detected. This gives us a feature vector reference that we can use to re-identify the object later, even if the motion track is lost. But it does this at the cost of adding complexity to our overall pipeline. So to support generating an appearance embedding, we now need to run 2 AI models. We need to run an object detection model, and now we need to run a second object embeddings generation model. We need to do these concurrently. And this will add to the re-identification capability, which will solve our motion tracking limitations, but it creates a new problem because now we have to generate an embedding for every object in the scene. And what this means is that as the scene becomes busier, more processing is required. So in other words, we've really kind of solved our problem by building ourselves a lovely little bottleneck. So just to jump back to this example, so even with a fairly simplistic example of motion tracking and tracking, we can see how code refactoring, timing, and synchronization headaches are going to add up quickly. And this is where pipeline flexibility can be leveraged to help rebalance the system or offload a bottleneck or extend a capability. And I can show you a quick demo of this. So you might use your propeller hats for this a little bit, but here's a console running on our Atlas hardware. This is running on NXP's i.MX 8M Plus CPU. On the top left is the command console. Underneath that is the performance of the video source node with stream input coming into the device at 25 frames per second. On the bottom left is the CPU utilization of the 4 ARM Cortex A53 cores in the i.MX 8M Plus running at 1.8 gigahertz. Then what we have on the right side is the performance of our tracking nodes. The top inference node is running a MobileNet V2 SSD model, which is performing object detection. The second inference node is running a MobileNet V1 model, performing the object embeddings. And on the bottom right is the analytics node running our re-identification and tracking analytics. Now, when I start this, it's going to be running everything on the 8M Plus CPU cores. But what we're going to do is we're going to use the flexibility of our pipeline architecture to offload the processing intensive inference nodes from the CPU to the 8M Plus NPU. So we can see from the analytics output in the bottom right side that the system is running at about 3 frames per second. This is bottlenecked by the inference models above. What we'll do is we'll now reconfigure the pipeline. And to make this change, all we need to do is edit a couple of JSON config files for each of the inference nodes. First, the object detection inference node, which we're doing now, change it from CPU to NPU. And then we'll do the same thing for the embeddings node. We'll change that from CPU to NPU. We'll just save it. And we'll now orchestrate the new pipeline using Docker Compose. And what will happen is we'll go through a few seconds of what is called NPU warm-up time. And we'll see on the right side in a couple of seconds, once the NPU warm-up is done, the inference node will start to see a performance uplift first. And there it goes up to about 24 frames per second. And the object embeddings inference node will just complete warm-up as well. And we'll see a performance uplift on that too. And then finally, we can see now the analytics node is performing at about 24.9 frames per second, which is equivalent to our input frame rate. So essentially, we're performing this entire pipeline at line rate. We can also see that the CPU utilization has also dropped considerably. So the point is here that this architecture facilitates experimentation. It decreases the amount of code that needs to be written and maintained to do that. And it delivers a method to discretely upgrade pipeline components easily to service them in the field. It also provides the extensibility to offload bottlenecks or even add significant new capabilities just by changing a couple of characters in the JSON config file and running Docker Compose. So in this case, all of the processing was done locally on the i.MX 8M+ CPU, but because the pipeline is interconnected using sockets, we could have just as easily offloaded it to another SoC, a device, an edge server, or even a cloud server. So let's switch gears now from talking about enablement to talking about hardware, because having all of this flexibility in software is great, but you need to have hardware that can also support it. This is our Atlas Scalable Edge AI platform. This uses NXP's i.MX 8M+ with optional additional acceleration provided by NVIDIA. It scales from 4 up to 10 ARM V8 cores and can scale from 2.1 to 23 TOPS of AI acceleration. This platform's got lots of I/O. It's got dual HDMIs. It's got GPIO. It's got lots of options for mass storage and connectivity. And as you can see by the form factor, it's set up to be an edge unit and not a camera, which makes it ideal as an analytics gateway or edge node or to be built into equipment, such as a smart kiosk or signage or a vehicle or industrial equipment. In terms of overall performance, this chart illustrates frames per second running real-world models. We believe that FPS is a good metric because it considers not only the inference time, but it also includes the pre and post-processing time, which can be considerable overhead. The column on the left is the CPU-only performance of a quad-core A53 CPU. It's running MobileNet V3 small SSD. We're just providing that as a reference. The 3 columns to the right represent the different hardware configurations of Atlas running quantized MobileNet V2 SSD models, starting with the Aqua column, which is the 8M+, and then adding different NVIDIA acceleration on top of it, scaling it from 62 frames per second all the way up to 187 frames per second. Now, there's not a lot of applications that may require 187 frames per second, but what this illustrates is the headroom for more sophisticated processing pipelines or scalability to process multiple video streams concurrently, which would be ideal for an analytics gateway unit. Okay, I've covered enablement and hardware, and that leaves us with the fun stuff, which is analytics applications. We have a broad portfolio of analytics. Here is just a few examples, and these can be used as is, or leveraged, or customized to build highly customized solutions. On the top left, this is a fairly straightforward zone incursion and boundary crossing application with people counting and tracking. On the top right is our package analytics. It can be used to secure packages and can also detect abandoned packages and who owns them. And then on the bottom row, we get a bit more sophisticated with behavior analysis, which can range from simple loitering detection to much more sophisticated applications, including action recognition. And then finally, characterization, which describes anonymized appearance attributes such as clothing, age, or gender. And I can show you a quick demo of what characterization is and how it can be applied. So in this particular demo, we're characterizing what a person is wearing, which is useful if you're trying to locate a specific individual, but it can also be used in environments where it's possible to distinguish what people wear, distinguish people by what they wear. Healthcare is a good example of this, where you can distinguish doctors, nurses, and orderlies, all because they wear distinct uniforms. So to run this analytic, we actually run 3 models concurrently. So we run an object detection model that detects people. We run an embeddings model to give us the robust tracking that we need. And then we run a segmentation model, which is a heavyweight model that provides the probability of each pixel in the frame and the probability that it belongs to a certain article of clothing, a certain class of clothing. Then we combine all of this insight together to provide a unique ID and the clothing characterization. And this example of characterization is as a straightforward analytic, just with the raw output. But when it's applied to an application and workflow, this can actually transform into a powerful tool. And that's what I'll illustrate here. This UI UX is part of our Brink solution. It's running on our Atlas platform. It's very complete. It has live and playback modes. It's got incident notifications. It's got an event timeline. In this case, to illustrate the capabilities of characterization, what we've done is we've added 2 features to it. We've added an active watch list function that provides a notification when someone who matches a description appears in the live video. And we've added a smart search function that will find people that match a description from within the timeline. And in this case, what we're going to do is we're going to use the smart search function to look for a lost intern wearing a green shirt. So with the smart search function, we're going to enter the characteristics of what the person is wearing that we're looking for. In this case, it's going to be a green shirt. We're going to start the search, and this is going to return us a list of events from the database that match the search criteria from within the timeline range that we have selected. We can then click on one of these results, and there he is. We've found our lost intern. And while this characterization example is limited to clothing, characterization certainly isn't limited just to clothing. It's fairly easy to see how this could extend to makes and models of vehicle. We can also characterize age and gender, which is really critical for retail applications. And these can even be combined together to form some really interesting insights for much more specialized applications. So that's it for my portion of the presentation. Hopefully I've given you some good insight in what it takes to build an edge AI solution and the capabilities that you can think about. Of course, once you've built the solution, the next logical step is to secure it. And we have just the guy to talk to you about that. So let me hand things over to Steve Chappell from Synopsys.
Great, thanks, David.
Steve, you should have control, but let me know if you don't.
I do. Okay. So thanks very much. We've built up a great platform and framework here. The hardware, the OS, some of the very cool ingredients are all here. And now we need to develop the software to pull everything together and provide a user experience on top of all this goodness. So just like if you're protecting your home, you can do all your research, get the best system, the best components, the best monitoring service. But if you don't teach your kids to close their windows and set the alarm before they leave, or the cat sitter drops the sticky note they wrote your alarm and door code on when they leave, it's kind of all for nothing. So, or maybe more apropos, detecting the UPS driver to open up your garage is great, but the copy paste error that left the garage door open despite showing in your app that it was closed is probably going to be a problem. So how do you secure the stuff that you bring to the table, to steal the device model here, your application layer, any of the other software components that you may be modifying or configuring in your own particular way, so that you can really set your products apart. And Reed talked earlier about the fragmentation and complexity in the space, and that's really evident in all of the languages that are used, the deployment methods and locations, and the communication mechanisms, right, between all of the software components. And edge and IoT systems are a great example of bringing all of those disparate and complex systems together. So how do we understand this and build up a plan? So all apologies to Chris Berman. This will be like the fastest 10 minutes in software security. Let's talk a little bit about what it means to do a threat model. We also need to understand the overall supply chain. Where are we getting all of our code? From both vendors, from open source, are we scanning all of the containers and the container images that are coming in, all the different artifacts? Then we also need to make sure that we analyze all the things that we've touched or developed, all the source code or anything else that has the word code in it, right? Even infrastructure as code now are things that we want to actually scan and look at. So, understanding Helm as you're spitting out all these resources in your edge system, and having specific checks for them is going to be very important. And then once you've actually analyzed all that code, let's actually go and try to break it, ideally in as few cycles as possible. And so I will talk about a couple of, there's a lot of different ways of doing this, but I'll talk about a couple of key technologies that I think people may not be as aware of, to give you some hints around that. So starting with that threat model is really about understanding all of the attack surfaces that you have within the overall system. So, you've got your edge system. How are the IoT devices talking to it? You've got the IoT devices themselves. You've got the mobile application. You've got the web UI. Each of those are written in different languages, probably. The lower level ones may be written in C, C++. You've got higher level languages for some of the others. And then you've got all the arrows in between. What are those protocols? How is the IoT device actually giving information up to the edge, and how is the edge then communicating up to the cloud and all the systems up there? Are those going over APIs? Are they going over gRPC or some other proprietary protocol that you've developed? And then finally, what are the other use cases, right? What are the attack vectors that are possible, from the over-the-air updates, once the system's actually in place? So understanding all of this, getting them all into a document and then into a plan that you can then cover is super important. This is what we call a threat model. I know if you've never done a threat model before, I highly recommend having someone help you with that. Or even if you've done hundreds of these threat models, getting that fresh set of eyes to do one is really important and a great value add to bring in, to make sure that you've really covered everything and thought about all of those different services and vectors. So once we've developed that plan, right, we've identified all the components, let's start looking at some of the things that we're bringing in and really understanding and assessing the supply chain. This has come up quite a bit with the executive order you may have heard about that came out earlier this year. Everyone needs to have this software bill of materials. Where is everything coming from? How do we secure the overall software supply chain? And let's focus a little bit on the open source piece of that. And open source is an amazing differentiator. It's an amazing productivity gainer, right? Because you don't have to rewrite everything from scratch. You just want to go to and grab something that's already been written, already been proven out, and use it. Same reason that you're buying IP from certain companies, because you can't do all that stuff from scratch. But a lot of times there's even more open source than you think you have in your overall code base or in the artifacts that you're providing. They come in not just through those approved components, the ones that you intended to download, but there are transitive dependencies that come in as well. So those components, pulled in other components, which pulled in other components. As you're, deploying things in containers, that is something that you need to understand and make sure that the base images of those containers are all scanned as you spin them up. So because those are bringing in additional open source that you may not be intending to. Because along with all of those open source goodness comes some security and potential license risks along with it. So there are known vulnerabilities, that have been identified for different packages and versions. So the first step is really to have some tool in place, right? Nobody can do this anymore with just a spreadsheet of tracking the things that they think are in their system. You actually need to go and analyze the code base and analyze all the artifacts that you're sending out. You do that by scanning the code base in multiple different ways. You need a tool that can scan not just the package managers and the manifest files. I see a question from everybody. Is everybody hearing me still? Peter, are you still hearing me?
Yep, we can hear you, Steve.
Yes.
Okay.
Yes.
So just the person that chatted, just making sure. So you, not just the package managers and manifest files, but also doing signature scans, because especially if you're working in a language like C or C++ that doesn't have package managers, you need to be able to detect the code. You also want to be able to see through signature scans whether the code that you've pulled down has been changed since it was scanned on the source, on the forge, right? So looking for places where either things were intentionally or unintentionally changed or injected, potential malicious code injection, or just you've added something or changed something. Having that understanding is key. So building out that full software bill of materials through multiple detection engines, then you can start doing the protection part. Protecting from known vulnerabilities, you map all those components and versions that you found to known vulnerabilities. One other key is not looking just in the National Vulnerability Database, but having a security team that is doing its own research, validating all of the vulnerabilities, and providing real mitigation guidance. Not just, hey, here's the CVE number, but here's a workaround if you can't update to the latest version, right? So that stuff comes with a great knowledge base and a security team. There's the license risk associated with those also, knowing if these are copyleft licenses or permissive ones. And then the last piece is making sure that the system or the tool that you're using, you don't have to rescan everything. It keeps that bill of materials around so that you know which components are in which versions of your products that you've shipped, so that if there's a new vulnerability that's been discovered, you automatically get notified, and then you can notify your customers as well. Very quickly, now that we've looked at all the stuff that we didn't write, let's look at the stuff that we did write. And if you want to do, you need to do static analysis of all of this code. And a lot of the tools today, we'll cover one or two languages. There's open source options for a lot of these, but if you want to get the most bang for your buck, get one tool that supports all the languages that you are writing in for the device, the edge, the cloud, and infrastructure as code, and also supports all the frameworks that you're using. Being able to support these frameworks really helps in terms of reducing the number of false positives, increasing the accuracy of the analysis, and also increases the performance of the analysis, because you don't have to either reevaluate that framework or do some guessing if those models are already built. And there are custom checks for those frameworks in there, that are very specific to, say, the Android operating system or the CUDA language that you are using for your AI implementation. So making sure that all those things are supported within your static analysis tool, and not having to switch between 20 different static analysis tools to cover each of those languages is going to save you a lot of headaches down the road. last piece, try to break it. So you can always use some penetration testing services on either the devices, the web apps, the APIs, thick client testing on some of these embedded devices. But a couple of technologies that I just want to highlight very quickly: fuzzing the protocols of how these things are communicating and test the robustness of the system. This is one of the key attack vectors for a hacker, right? Let's flip some bits in the HTTP protocol or the MQTT protocol, or flip a bit in Zigbee or Wi-Fi and see what happens, right? So that's what fuzzing is unexpected input and observing the response and the effects. If you've got models of all of these built up, which we do in a product that we have called Defensix, it's very easy for us to get very deep into the state machines. You get through all of the handshake levels, and then you put in some anomalous code. So supporting Zigbee, supporting Bluetooth and 5G and some of these other communications protocols between the IoT device and your edge is super important and very easy with a tool like Defensix. And then we've talked a lot about containerization, and building up these systems with microservices is key now too. So if you haven't heard of or used IAST, which is interactive application security testing, it's a way of instrumenting the services or microservices that you've deployed and getting visibility into them in a test environment. One of the key benefits of that is it can, for a tool like Seeker is an IaaS tool that will watch all the transactions that are coming and actually replay them with fuzzed payloads, so that you can detect real vulnerabilities. So you get a zero false positive rate because it actually sees, and can reproduce these. But it also has the productivity game of changing all of your functional tests into security tests. The other key piece that you get from this is the visualization of the data flow and the traffic between all the microservices, as well as finding all the internal and external APIs that are being called by your services or microservices. So this feeds into that threat model all the way from the beginning of how do I know what are all the APIs that I'm both calling and presenting. So that's super important, very useful, great productivity gain. And it's, again, something that is very easy to deploy. So I could talk for hours on a more complete application security portfolio. I'll just leave it as, if you have more questions, we're available, ask us. But I hope that quick 10-minute primer was enough to get the juices flowing, so that you can secure the software piece of all this great goodness.
Thank you, Steve. I know that was difficult to do in 10 minutes, so we'll wrap up here with a summary and then head into the Q&A. So by now you're familiar with the framework. Thank you for all the presenters. I know it's difficult to cram this into an hour or so, but if you do want additional information, there'll be additional links on all of these that go into more depth. And just to wrap up with the summary, Reed from ARM talked about the foundation for secure IP and hardware and software with the platform security architecture, Project Cassini, Parsec, and system ready initiatives. Ali from NXP spoke about how NXP builds on this foundation with IMX processors, the new ARM Ethos MPU, and NXP's EIQ machine learning software. This enables new levels of compute power and efficiency. Scott from Siemens talked about how Siemens can enable a secure and robust commercial grade Linux OS with security management and control, an IoT framework, and containerized app deployment with remote device management. David at Arcturus showed a powerful AI ML edge vision platform based on ARM's NXP. This will help you to speed your software and time to market. And then finally, Steve from Synopsys showed how you can secure your application with code, containers, and interfaces with the industry's most complete security portfolio, application security testing, fuzzing, threat modeling to help you reduce your risk and enable trust. So with that, I'll hand over to Mike for Q&A.
Hi, everybody. Thanks for joining today. We do have a few questions. I did want to point out again, that the link will be available within the next 3 business days to download the presentation and view the video. And that will come to you from Zoom, directly from Zoom. The first question, well, we had a few other questions that have been answered, but I'll walk through them in a minute. But the one that's still open is, what exactly is TensorRT and what does it do? And that's for David Steele.
Sure, I can cover that one off. TensorRT is a runtime, much like TensorFlow Lite is a runtime, and ARM and is a runtime. TensorRT is specific to NVIDIA's GPU ecosystem. So simply put, it's NVIDIA's runtime, Edge AI runtime.
Okay, thanks, David. The other questions that the other question that I have here right now is, who can address ISVs using Trust Zone, TEE SDKs, Tristonic, Qualcomm to build containerized or non-containerized trusted applications that run on IoT, mobile, cloud platforms, wish to move workloads securely amongst IIoT, mobile cloud platforms, and maintain guaranteed TEE isolation. Still attempting to understand the secure SDLC and tooling needed. So that was from Kevin, and you'll get, as part of the landing page, there'll be a place for the questions. Reed's going to have to answer that. There are a couple of links, and maybe Peter, you could put those in the chat if you can see them. That would be great.
Sure.
Yeah, Kevin, if you're still on the line, I put my email address in here, but it's just read@hinkel@arm.com. And I can send you the link. We actually had a white paper and blog that we did with Microsoft Azure IoT group around a Edge Enclave blueprint that actually talks through some of the issues that you mentioned. Not leveraging the proprietary trust execution environments, but actually leveraging Opti, which is a open source trusted execution environment that's actually part of ARM trusted firmware and used by many of our silicon partners as part of their SDKs and BSPs for their platforms, including NXP. So the Enclave blueprint was actually done on a Layerscape 1028, which is from NXP. So it'd be a companion or another line of processor products from NXP, kind of a sister product to the IDOM X8 family.
Thanks, Reed. Another question, I'm guessing this is for Arcturus. How does the Arcturus Atlas work? And it has 2 ARM processors, one from IMX and the second, the NVIDIA IC. How does this platform work? Do you need to install 2 Linux on each of the 2 Linux operating systems on each of them, or is it somehow implemented to work with access from one processor to another?
So that's a very good question. So it is scalable. So the first thing we have to sort of think of is that it can run just with IDOM X8M Plus by itself, if that's what the needs of the Edge AI require, or it can scale up with additional SoCs. The backplane that interconnects all of that, so the fabric on the back end is actually a network fabric. So we interconnect it using sockets, as I kind of illustrated in our pipeline example. So both of those SoC devices are running full Linux stacks. But the advantage to that is that then you have lots of places where you can build additional applications, whether that's on the 8M Plus part or the NVIDIA part, and then have those all interconnected through a private network, which is that backhaul fabric on the device.
Thanks, David. And in the interest of time, we do have some questions that were answered, but we have run over, and we'll get you those answers. You'll be able to take a look at them and download them in an Excel spreadsheet with the link that gets sent from Zoom in a couple of days. I think that wraps everything up. If there are no other questions, short ones. And we'd like to thank everybody for joining today. Thank all the participants and the panelists. That was a great job. Greatly appreciated from everybody. And we hope everybody has a great holiday season. And if there are any further questions, you can reach us through Zoom, the email. There will be a link there to an email for Electrosource, and we can coordinate with anybody and get you some additional information if required. So thank you, everybody, and have a great holiday.
Thank you for hosting.
Thanks, everybody.
Thanks.
Thank you,
Everyone.
Thank you,
Bye.
everybody.
Thank you, everybody.
Thank you.
Bye.